determine the correct supply conductor size for a motor, refer to Article 430 of the National Electrical Code, or NEC. Tables 430.249 and 430.250 provide allowable ampacities based on insulation type, ambient temperature, and usage conditions. For a 12 AWG conductor with type THHN insulation at 40 degrees Celsius ambient temperature, the allowable ampacity is 25 amps. The motor in question has a starting current of 49 amps and a running current of 11.2 amps. The 12 AWG conductors are inadequate for the starting current. Therefore, larger conductors are necessary. Since the motor is internally thermally protected, additional protection isn't required unless specified by the manufacturer or the NEC. However, a circuit breaker is generally recommended. A circuit breaker protects the motor from overcurrent conditions caused by excessive load or short circuits. Size the circuit breaker to the motor's running current of 11.2 amps. An overload relay is also recommended. This prevents the motor from overheating due to overloading or other abnormal operating conditions. Set the overload relay to trip at the motor's running current. Consider a motor starter. It reduces the starting current and provides additional motor control. Soft starters or variable frequency drives, or VFDs, can further reduce the starting current. Based on the motor's 49 amp starting current, 10 AWG conductors with type THHN insulation would be the minimum acceptable size for the supply circuit. Always consult a qualified electrician for specific installation requirements. The NEC specifies requirements for motor circuit conductors and overcurrent protection to ensure safety and prevent damage. Article 430 provides detailed guidelines for selecting the appropriate conductor size, overcurrent protection devices, and other components based on the motor's characteristics and application. Firstly, calculate the motor's full load current, or FLC, from the motor nameplate. This value is used to determine the minimum ampacity of the supply conductors. Secondly, Table 430.248 and 430.250 in the NEC provide the FLC values for alternating current, or AC, single-phase and three-phase motors respectively. These tables are used if the motor nameplate FLC is not available. Thirdly, the minimum ampacity of the motor supply conductors is typically 125% of the motor's FLC. This accounts for the continuous duty operation of the motor. Refer to NEC section 430.22. Fourthly, select a conductor size with an ampacity equal to or greater than the calculated minimum ampacity. Use NEC table 310.15b16 to determine the allowable ampacity of different conductor sizes and insulation types. Fifthly, correct the allowable ampacity of the conductors for ambient temperature and the number of current carrying conductors in a raceway or cable per NEC 310.15. This ensures the conductors can safely carry the current under the specific installation conditions. Sixthly, size the motor branch circuit overcurrent protection device, typically a circuit breaker or fuses, to protect the motor, conductors, and other circuit components from overcurrents due to short circuits or ground faults. Seventhly, the maximum rating of the overcurrent protection device is determined by NEC section 430.52. This section provides different percentages of the motor's FLC based on the type of overcurrent protection device used, such as inverse time circuit breakers or fuses. Eighthly, for inverse time circuit breakers, the maximum rating is typically 250% of the motor's FLC, unless the calculated value does not correspond to a standard size circuit breaker. In that case, the next higher standard size is permitted. Ninthly, overload protection is also required to protect the motor from damage due to excessive overload conditions. Overload protection devices, such as thermal overload relays, are designed to trip and disconnect the motor from the power supply if the motor draws excessive current for an extended period. Tenthly, NEC sections 430.31 through 430.43 provide requirements for motor overload protection. The overload protection device is typically sized at 125% of the motor's FLC for motors with a service factor of 1.15 or higher, or a temperature rise of 40 degrees Celsius or less. In cases where the overload protection device trips nuisance, it is permitted to increase the size of the overload protection device to a maximum of 140% of the motor's FLC. However, this should be done cautiously to ensure the motor is adequately protected. The motor's nameplate provides important information for determining the proper conductor size and protection requirements. This includes the motor's voltage, full load amps, frequency, horsepower, and service factor. The motor's voltage rating must match the supply voltage to ensure proper operation. Full load amps, or FLA, is the current the motor draws when operating at its rated horsepower and voltage. This value is used to determine the minimum ampacity of the supply conductors and the size of the overcurrent protection devices. The motor's frequency, typically 60 Hz in the United States, must match the frequency of the power supply. The motor's horsepower rating indicates the mechanical power the motor can deliver. The service factor is a multiplier that indicates the motor's ability to handle occasional overloads. A service factor of 1.0 means the motor can operate continuously at its rated horsepower, while a service factor greater than 1.0 indicates the motor can handle occasional overloads without overheating. Motor starters are used to provide a reduced voltage starting method to limit the inrush current during motor startup. Reduced voltage starting methods such as autotransformers, reactors, or solid-state starters reduce the voltage applied to the motor during startup, which reduces the inrush current. This helps prevent voltage dips and reduces stress in the motor and connected equipment. Variable frequency drives, or VFDs, are used to control the speed and torque of AC motors. VFD provide adjustable speed control, energy savings, and improved motor performance. They convert the incoming AC power to direct current, or DC, and then invert it back to AC at the desired frequency and voltage. This allows precise control of the motor speed and torque. Grounding is essential for motor circuits to provide a low impedance path for fault currents and protect personnel from electric shock. The equipment grounding conductor, or EG, connects the motor frame and other non-current carrying metal parts to the grounding system at the service equipment. This ensures that any fault current will quickly trip the overcurrent protection device, disconnecting the power supply and preventing electric shock hazards. Bonding is also important to ensure that all metal parts of the motor circuit are electrically connected to create a low impedance path for fault currents. Bonding jumpers are used to connect metal raceways, enclosures, and other metal parts to the grounding system. This helps to minimize voltage differences and reduce the risk of electric shock. The NEC provides specific requirements for grounding and bonding of motor circuits in Article 250. These requirements must be followed to ensure a safe and effective grounding system. Proper installation and maintenance of motor circuits are essential for reliable and safe operation. Conductors should be properly sized, terminated, and supported. Overcurrent protection devices should be correctly sized and tested to ensure they operate properly. Grounding and bonding connections should be tight and free from corrosion. Regular inspections and maintenance can help identify and correct potential problems before they lead to equipment failures or safety hazards. When working on motor circuits, always follow safe work practices. To energize and lock out the circuit before working on it. Use appropriate personal protective equipment, or PPE, such as safety glasses, gloves, and insulated tools. Be aware of potential hazards, such as exposed energized parts, and take steps to mitigate them. If you are not qualified to work on electrical equipment, seek assistance from a qualified electrician. The information provided here is for general guidance only and should not be considered a substitute for professional electrical advice. Always consult with a qualified electrician or refer to the NEC for specific requirements and recommendations for your application. Motors are critical components in many industrial and commercial applications. Ensuring that motor circuits are properly designed, installed and maintained is essential for reliable operation, energy efficiency, and safety. By following the guidelines in the NEC and working with qualified professionals, you can ensure that your motor circuits meet the highest standards of performance and safety. Furthermore, consider the ambient temperature when selecting conductors. High ambient temperatures can reduce the ampacity of conductors, requiring larger conductors to be used. The NEC provides correction factors for ambient temperatures in Table 310.15b2. Also, consider the number of current-carrying conductors in a raceway or cable. When multiple current-carrying conductors are installed in a raceway or cable, the ampacity of each conductor must be derated according to NEC Table 310.15b3. This is because the heat generated by the conductors can raise the temperature inside the raceway or cable, reducing the ampacity of the conductors. Additionally, select conductors that are suitable for the environment in which they will be installed. For example, conductors installed in wet locations must be listed for wet locations. Conductors installed in corrosive environments must be resistant to corrosion. The NEC provides requirements for conductor types and applications in Article 310. It's important to properly terminate conductors to ensure a reliable and safe connection. Use appropriate connectors and tools for the conductor type and size. Follow the manufacturer's instructions for terminating conductors. Improperly terminated conductors can overheat, leading to equipment failures or safety hazards. Also, consider the voltage drop in the motor circuit. Excessive voltage drop can reduce the motor's performance and efficiency. The NEC recommends limiting the voltage drop in motor circuits to 5%. To minimize voltage drop, use larger conductors or reduce the length of the circuit. Selecting the correct overcurrent protection device is critical for protecting the motor, conductors, and other circuit components from overcurrents. Overcurrents can be caused by short circuits, ground faults, or overloads. The overcurrent protection device must be able to interrupt the fault current before it causes damage. The NEC provides requirements for overcurrent protection in Article 240. Fuse sizing requires selecting fuses with the appropriate current rating and interrupting rating. The current rating of the fuse must be high enough to carry the normal motor current, but low enough to protect the conductors and motor from overcurrents. The interrupting rating of the fuse must be high enough to safely interrupt the maximum fault current that could occur in the circuit. Circuit breaker selection involves choosing circuit breakers with the appropriate current rating and interrupting rating. Circuit breakers are available in various types, including thermal-magnetic instantaneous trip and electronic trip. Thermal-magnetic circuit breakers provide both overload and short-circuit protection. Instantaneous trip circuit breakers provide only short-circuit protection. Electronic trip circuit breakers offer adjustable trip settings and advanced protection features. Overload relays are used to protect motors from damage due to excessive overload conditions. Overload relays are typically thermal or electronic. Thermal overload relays use a bimetallic strip that bends when heated by the motor current. When the bimetallic strip bends sufficiently, it trips a set of contacts disconnecting the motor from the power supply. Electronic overload relays use a current transformer to sense the motor current and an electronic circuit to monitor the current level. When the current exceeds a preset threshold, the electronic circuit trips a set of contacts, disconnecting the motor from the power supply. In addition to the requirements in the NEC, local codes and regulations may also apply to motor circuits. Be sure to check with your local authorities to determine any additional requirements. Motor control centers, or MCCs, are commonly used in industrial facilities to house motor starters, overcurrent protection devices, and other control equipment. MCC provide a convenient and organized way to control and protect multiple motors. They also offer features such as remote control, monitoring, and diagnostics. Power factor correction capacitors can be used to improve the power factor of motor circuits. Power factor is a measure of how efficiently electrical power is used. A low power factor can result in increased energy consumption and reduced system capacity. Power factor correction capacitors can improve the power factor, reducing energy costs and improving system performance. Harmonics or distortions in the electrical waveform that can be caused by nonlinear loads such as variable frequency drives and electronic equipment. Harmonics can cause overheating of equipment, interference with communication systems, and other problems. Harmonic filters can be used to reduce harmonics in motor circuits. Surge protection devices, or SPDs, are used to protect motor circuits from voltage surges caused by lightning, switching transients, and other events. Voltage surges can damage sensitive electronic equipment and cause motor failures. SPD diverts surge current to ground, protecting the equipment from damage. Regular inspections and testing are essential for maintaining the reliability and safety of motor circuits. Inspections should include checking for loose connections, damaged insulation, and other signs of wear and tear. Testing should include measuring insulation resistance, checking overcurrent protection devices, and verifying grounding connections. Proper documentation of motor circuits is important for troubleshooting and maintenance. Documentation should include wiring diagrams, equipment specifications, and test results. This information can help technicians quickly identify and correct problems. Energy-efficient motors can save energy and reduce operating costs. Energy-efficient motors are designed to operate with higher efficiency than standard motors. They typically have lower losses and generate less heat. When replacing a motor, consider using an energy-efficient motor to save energy and reduce operating costs. Predictive maintenance techniques can be used to identify potential problems before they lead to equipment failures. Predictive maintenance techniques include vibration analysis, infrared thermography, and oil analysis. These techniques can help detect early signs of wear and tear, allowing technicians to address problems before they become serious. Ultimately, always prioritize safety when working with electrical equipment.